Welcome to the Deep Dive. Today we're tackling something that sounds straight out of sci-fi, but it's very real and driving huge growth.
Absolutely. We're talking about technology projected to hit, over $110 billion in market value pretty soon.
Exactly. We are talking about the digital twin.
And it's really fundamental now. Forget simple models. A digital twin is like a living virtual copy.
A living copy.
Of what exactly?
Of a physical thing or a process, even a whole system like a factory or a city. And the key is it's constantly updated.
Updated with real-world data.
Continuously, yeah. So you can run simulations, do analysis, make predictions in real time. It's like a dynamic software mirror of the physical world.
A living mirror. I like that. And yeah, that market size shows this isn't just some niche experiment anymore.
Not at all. It's core to industrial innovation now.
So our plan today is to trace this whole story. How do we get from, basic physical models in the space race to these incredibly complex virtual systems? Right. We'll cover the history, the tech behind it, the nuts and bolts, and then look at some really specific, kind of surprising examples across manufacturing, healthcare,
smart cities, energy, the works.
Exactly. The mission is to figure out how we made that leap from, say, physical mock-ups for spacecraft to simulating a living human heart or managing a city's power grid.
Okay, let's unpack this then. And I guess the most dramatic place to start isn't digital at all, is it? It's NASA.
That's right. The core idea, this concept of twinning, having a mirror you can safely experiment on, really took shape during the Apollo program back in the 1960s.
And they weren't using software, obviously. They had physical duplicates.
Physical duplicates, yeah. And incredibly complex simulators on the ground, basically hardware mirrors of the key systems flying in space.
Which brings us to Apollo 13. That's the story everyone knows, the ultimate terrifying test case.
It really is. 1970, the crisis hits, the service module is damaged, and the engineers on Earth weren't just guessing. They had those simulators, their physical twins.
So they could replicate the problem.
Painstakingly. They updated their ground models, the command module mock-up, the lunar module to match the exact conditions on the crippled spacecraft, power levels, temperature, the damage.
They mirrored the failure state right there in Houston.
Precisely. So they could test solutions. That famous CO2 filter fix. They figured that out on the ground first, using the parts available to the astronauts.
Testing it in the simulator before radioing up the instructions.
Exactly. Same for the critical engine burns needed for re-entry. They rehearsed it all on their twin. It proved the immense value of having that synchronized physical representation, even if it wasn't digital yet.
Makes total sense for something as high stakes as space travel. But, okay, moving from that physical mock-up to a digital software version, that took a while longer.
It did. The conceptual groundwork for the digital side really started to appear in the late 80s, early 90s. You have to look at computer scientist David Gelernter.
Gelernter. And his idea of mirror worlds, right? That name always stuck with me.
Yeah, it's very evocative. In 1991, he described these software models of reality, but the key was they'd be fed by constant, ubiquitous data streams.
So not static models, living models, even back then conceptual.
Exactly. He envisioned them constantly refreshing, capturing all the relevant details of the physical world they represented. It was a really crucial insight, the need for continuous data integration. That's the bedrock of the modern digital twin.
Okay, so the seed of the idea, the continuous data link, was planted in the early 90s, but the actual term digital twin, that came later.
It did. The term itself and the formal definition, that really solidified in the early 2000s, thanks to Dr. Michael Greaves.
Greaves, right.
He presented the model formally in 2002. Interestingly, he didn't call it a digital twin at first. His term was the information mirroring model.
Information mirroring model. Doesn't quite roll off the tongue the same way.
Not quite. But he wasn't just naming it. He was laying out the architecture, the fundamental components.
And what were those? What makes it different from just, say, a CAD model or a regular simulation?
He defined the three pillars, which we still use today. 1, the physical thing, the asset. 2, its virtual representation, the model.
Okay.
And 3, this is the absolute key, the data connections linking the physical and the virtual. That link has to be robust, dynamic, often real-time, and usually bidirectional.
Bidirectional, so data flows both ways.
Often, yes. The twin gets data from the physical asset, but it can also send instructions or insights back. Without that third pillar, that dynamic connection, it's just a static model. The twin has to be alive.
That continuous sync.
Yeah.
That's the game changer. And NASA picked up on this formalized concept pretty quickly.
They did. They saw the potential immediately for managing spacecraft health, predicting problems. It showed up in their tech roadmaps from around 2003 to 2010.
And military too, I imagine. Complex assets, high maintenance costs.
Exactly, which leads to that well-known Air Force example.
The F-16.
Yes. By 2010, the U.S. Air Force had developed a pretty sophisticated digital twin for the F-16 fighter jet. This wasn't just a 3D picture. It was a virtual aircraft that tracked everything.
Like flight hours, stress, repairs.
All of it. For each specific aircraft tail number. This let them shift from fixed maintenance schedules, service after X hours, to condition-based maintenance, driven by the twins' data.
Which means optimizing repairs, saving money, keeping planes safer.
Drastically improving planning and lowering the total cost of ownership. It's a perfect bridge to the next phase, really.
Right, the 2010s, Industry 4.0. This is when the digital twin concept kind of exploded out of aerospace and defense, right?
Yeah.
Into general industry.
It really did. And it was fueled by this convergence of technologies, primarily the rise of the industrial Internet of Things, the IoT.
The sensors everywhere.
Right. Exactly. Suddenly, factories, supply chains, power plants, they were getting blanketed with millions of relatively cheap sensors, pumping out data constantly. That data fire hose was what was needed to feed those connections Greaves talked about.
So the IoT solved the practical data problem, and manufacturing jumped on it first.
Manufacturing led the charge, definitely. The ROI was just so clear. By around 2015, studies show something like 75% of advanced manufacturers were already using digital twins at some level of complexity.
And the big gains were in product development.
Initially, yes. Huge gains there. Think about cutting down the number of physical prototypes you need to build.
Right. You test virtually first.
You run hundreds, even thousands of design variations in the twin. Car companies doing virtual crash tests, for example. Instead of smashing 5 expensive prototypes, they simulate endlessly.
Which means faster design cycles?
Faster cycles, like 20 to 50% faster. And better quality, too, maybe 25% fewer issues found later because you catch design flaws much earlier in the simulation phase.
Huge savings in time and money. And the twins themselves were getting more sophisticated by the late 2010s. You mentioned physics-based twins.
Yes, that's a really important evolution. Physics-based twins go beyond just analyzing sensor data. They incorporate complex engineering principles.
Like fluid dynamics, stress analysis.
Exactly. Finite element analysis, FEA, computational fluid dynamics, CFD, thermal modeling. These are computationally intensive models embedded within the twin.
And what does that allow? Why embed the physics?
Because it allows the twin to predict how the physical asset will behave under new conditions it hasn't actually experienced yet. It's not just observing, it's calculating future states based on the laws of physics.
That sounds incredibly powerful, but also computationally expensive.
Extremely, but the payoff is massive. Because if you can run these physics models fast enough, synchronized with the real world,
you can predict problems way ahead of time.
Even better, you can enable closed-loop control. The twin doesn't just predict a problem, it calculates the optimal correction and sends instructions back to the physical asset.
So the twin tells the machine how to adjust itself.
Right. Adjust a pump speed, change a turbine's blade angle, optimize a chemical reaction automatically. Based on the twin's predictive simulation, the system starts to self-regulate.
Wow. The virtual model actively driving the physical world, that's a major step.
It really is, and it highlights how crucial the underlying technology stack is. Which brings us nicely into, well, how these things are actually built today.
Okay, segment 2, the modern tech stack. How do you handle all that data, all that complexity?
It starts, unsurprisingly, with the data and the compute power. The absolute foundation is the IoT sensor network. We're talking sensors everywhere.
Not just temperature and pressure anymore.
Oh no. Vibration, acoustics, chemical sensors, high-res video feeds, GPS, network data, everything relevant to the asset or process. And it's streaming constantly. Thousands, sometimes hundreds of thousands of data points per second for a single complex twin.
And managing that fire hose, plus running those complex simulations in real time.
Yeah.
That requires serious horsepower.
Absolutely, which is why the cloud is essential. You need that massive, scalable storage and processing power that most companies just can't afford to build on-premise anymore.
And specialized hardware, too, like GPUs.
Heavy reliance on GPUs, yeah. Especially for those physics-based simulations, CFD, FEA. They require huge amounts of parallel processing, which is exactly what GPUs are good at. Running those simulations fast enough to keep the twins synced with reality is critical.
So the cloud provides the muscle. What about actually building the virtual environment itself?
That's where specialized modeling and simulation tools come in. You often start with the detailed 3D CAD models, the engineering blueprints.
The geometry.
Right. And you import that into sophisticated simulation engines. Think platforms like Dassault Simulia, Siemens SimCenter, ANSYS. These tools handle running the physics calculations, simulating control systems, even modeling how humans might interact with the equipment in the virtual space.
Okay, so you have the data flowing, the compute power, the simulation tools.
Yeah.
But what makes the twin truly intelligent, predictive? That's where AI comes in, right?
Precisely. AI and machine learning are what elevate the twin from just a descriptive model to something predictive and even prescriptive.
How is AI used specifically?
Couple of key ways. First, analyzing those huge streams of sensor data. ML algorithms are fantastic at spotting subtle patterns that humans would miss, patterns that often precede a failure. That's predictive maintenance.
Predicting a breakdown days or weeks out, not just reacting when it happens.
Exactly. But AI also helps with the simulation speed itself, which is fascinating.
How? If a detailed physics simulation takes hours, how does AI make it real time?
Through something called surrogate models or reduced order models. Basically, you run thousands of those complex, time-consuming physics simulations offline.
Yeah.
Then you train an AI model, often a deep learning network, on the inputs and outputs of all those simulations. The AI learns the complex relationship between the inputs and the physics-based results.
So the AI learns to approximate the physics calculation.
Exactly. Once trained, the AI surrogate model can give you a statistically very accurate result almost instantly in milliseconds instead of hours. It's an approximation, but good enough for real-time decision-making.
That's clever. It makes the whole closed-loop control idea feasible.
Totally. And that's a big reason why you see stats like, roughly 75% of large companies are investing in digital twins specifically as a platform to deploy these kinds of flexible, AI-driven operational solutions.
And we should mention generative AI here, too. How's that changing the game?
Generative AI pushes twins beyond just mirroring what exists. It allows the twin to autonomously explore new possibilities.
Like designing a better product.
Yeah.
Or more efficient factory layout.
Exactly. You set the goals and constraints, and the generative AI within the twin environment can create and test thousands of novel design options or process configurations, potentially finding solutions humans wouldn't even think of. It's about accelerating innovation.
So with all this tech converging, it makes sense that big platforms are emerging to help companies actually build and manage these twins. Who are the key players?
You've got the major cloud providers stepping up with platform as a service or PaaS offerings. Microsoft has Azure Digital Twins, which is really strong on modeling the relationships between assets and system.
And Amazon.
AWS IoT TwinMaker focuses on pulling together data from various sources, IoT, video, business apps, to create operational twins, often of physical environments like warehouses or factories.
Then you have the industrial giants, the ones who know the machines intimately.
Right. Companies like GE Digital have leveraged decades of experience to create hundreds of predefined twin blueprints for specific assets, gas turbines, jet engines, wind turbines. They know the physics and failure modes inside out.
And IBM has something called the Digital Twin Exchange.
Yeah, that's interesting. It's trying to be a marketplace, a place where companies can find, buy, or even share standardized twin models or components, trying to accelerate development.
Which brings up a huge issue. With all these different platforms, Microsoft, AWS, GE, Siemens, Dassault, how do you make sure their twins can actually work together? Interoperability must be a nightmare.
It is the major challenge right now for wider adoption, absolutely. If your factory floor twin is built on platform A and your supply chain twin runs on platform B, getting them to share data and insights effectively is difficult and expensive.
So standards are needed. Badly.
Urgently. And there are groups working hard on this. NIST in the US, ISO internationally, industry bodies like the Digital Twin Consortium, they're all trying to define common languages, data formats, reference architectures.
Why is that standardization so critical for, say, a manufacturing company wanting to use twins?
Two main reasons. avoiding vendor lock-in and enabling scalability. You want to be able to plug together different twin components from different vendors without massive integration headaches.
Like building with Lego bricks instead of having custom-made pieces every time.
That's a good analogy. The goal is this idea of federation of twins, where an asset twin from one system can seamlessly connect and interact with a process twin from another system. They're also developing maturity models, ways to actually classify how sophisticated and capable a given twin is.
Okay, that framework makes sense. We've covered the history, the tech. Now let's get into the really tangible stuff. Segment 3, deep dive applications, starting with the pioneers, manufacturing and industry 4.0.
Right. As we said, manufacturing saw the benefits early, product development speed-ups, quality improvements. But the day-to-day impact is huge in operations, especially predictive maintenance.
How is twin-based predictive maintenance better than just, sticking a vibration sensor on a motor?
A simple sensor tells you vibration is high now. A digital twin of that motor takes the real-time vibration data, plus temperature, load, acoustics, everything.
Feeds it into that physics model.
Feeds it into its physics-based model, simulates the cumulative stress and wear on specific components, like bearings. Then, using AI, it predicts. Based on its current usage and wear rate, this bearing has a 90% chance of failing within the next 2 weeks.
So you fix it before it breaks down unexpectedly.
Exactly, avoiding costly, unscheduled downtime. But it scales way beyond single machines. Look at the BMW virtual factory case study. That's twin application at a massive scale.
They're twinning entire factories, over 30 of them globally. What does that even look like?
It looks like a highly detailed, centimeter-accurate 3D model of the whole plant. Every robot, every conveyor belt, every assembly station, even simulating the paths workers take. They use platforms like NVIDIA's Omniverse to render this, and crucially, they link it to real-time operational data from the factory floor.
So they can test changes virtually before touching anything physical, like planning a new car model launch.
Precisely. They simulate the entire new assembly process. Do the parts arrive on time via the logistics system twin? Do the new robots have enough clearance? Can they perform the task without colliding with anything or anyone?
That collision analysis must have been a huge manual effort before.
Weeks of work, physically moving mock-ups around, painstaking measurements. Now, in the twin,
How fast is it?
BMW reported that a complex collision check that used to take maybe 4 weeks can now be done in about 3 days using the twin's automated analysis. They projected savings of up to 30% in production planning costs just from this virtual validation.
30% reduction. That's a serious competitive edge. And the twin's job doesn't stop when the product leaves the factory, right? Thinking about jet engines?
The Rolls-Royce engine twin is a classic, powerful example of twinning for after-sales service and optimization. Every single engine flying has a digital counterpart.
Constantly receiving data during flight.
Hundreds of parameters per second. Temperature, pressure, vibration, speed, altitude, thrust settings, even atmospheric conditions, all feeding the specific twin for that specific engine serial number.
Why track each engine individually? Don't they know how the engine model behaves generally?
They do, but every engine wears differently based on how and where it's flown. Short hops in dusty environments versus long, smooth cruises over oceans. It makes a difference to component life.
So the twin personalizes the maintenance schedule.
Exactly. Instead of fixed conservative service intervals replace part X every 5,000 hours, the twin analyzes the unique operational history and predicts the actual remaining useful life of components for that specific engine.
Which lets them extend time between overhauls safely.
Significantly, sometimes by up to 50%. Huge cost savings for airlines. But it also enables performance optimization.
How so?
The twin data helps Rolls-Royce advise airlines on the most fuel-efficient ways to operate the engines for given routes and conditions, and the accumulated impact of that is massive.
You mentioned emissions reductions.
They estimated something like 22 million tons of CO2 emissions were avoided over several years purely through these twin-enabled operational efficiencies. It's cost-saving and sustainability hand in hand.
Really impressive linkage there. Okay, let's shift gears dramatically now. Segment 3.2, healthcare. Moving from machines to biology. The idea of the digital patient.
This is, for many, the ultimate frontier for digital twins, creating a virtual replica of an individual's unique biology, anatomy, physiology to simulate treatments and predict health outcomes just for them.
Truly personalized medicine. And the big milestone here is the Living Heart Project.
Absolutely. Led by Dassault Systems. It was the first really comprehensive, physics-based virtual twin of a human heart. It simulates electrical activity, muscle contraction, blood flow. Incredibly complex.
A functional model, not just a picture.
A functional multi-physics model. It took years of collaboration between medical experts, engineers, simulation specialists.
And the power is testing things in silico. We should probably explain that term.
Right, and silico just means in the computer, basically via simulation, as opposed to in vivo, in a living organism, or in vitro, in glassware, like a test tube.
So doctors or device makers can test treatments on the virtual heart first.
Exactly. Test different drugs, different dosages. Test medical devices like pacemakers or replacement valves. How will this specific valve design perform in this specific patient's heart geometry and blood flow? You can run thousands of virtual trials risk-free.
That's a game changer for developing and choosing treatments, especially with customizing the twin.
That's the next step, which is happening now. Using AI, you can take an individual patient's scans, MRI, CT, and their clinical data, and quickly personalize the generic heart twin.
Adjusting things like wall thickness, scar tissue, chamber size.
Exactly. So the surgeon gets a virtual copy of your heart. They can then practice placing that specific valve implant virtually, finding the optimal size and position before the actual surgery, reducing risks, improving outcomes.
And the FDA is involved, looking at using these simulations for approvals.
Yeah, there's collaboration there. The potential is huge. Could in silico trials supplement or even partially replace some lengthy, expensive physical trials for new devices? If you can demonstrate safety and efficacy across thousands of virtual patients, that could accelerate getting life-saving tech to people faster.
And it's not just hearts, right? People are working on twins for joints, lungs, even tumors.
All of those. Orthopedics is big, planning complex surgeries using patient-specific bone twins, respiratory models, and yes, oncology, the idea of a digital twin of a patient-specific tumor.
To test chemo combinations.
Exactly. Model its genetics, its blood supply, how it grows, then simulate hundreds of drug cocktails or radiation plans to see which is predicted to be most effective for that specific tumor profile. Hyper-personalized cancer therapy.
Amazing potential. But twins in healthcare aren't just personal, they're operational too, optimizing the hospital itself.
Yes, that's a really practical application gaining traction. Building twins of hospital workflows, the emergency department is a classic example.
Simulating patient flow, staffing, bed use.
All of it. You feed the twin real-time data, patient arrival rates, acuity levels, which doctors, nurses are on shift, which beds rooms are free, how long procedures take. It creates a dynamic simulation of the whole chaotic process.
And you use that to find the bottlenecks.
Find the bottlenecks and then test potential solutions virtually. What happens if we add another triage nurse during peak hours? What if we change the pathway for stroke patients? You can run experiments in the twin without disrupting the actual ED.
There was a Canadian study on this.
Yeah, they used an ED twin to test different staffing and flow strategies, found they could significantly cut waiting times, I think it was around 15%, just by making evidence-based tweaks identified in the simulation.
And COVID-19 must have really pushed this forward.
Absolutely. Hospitals worldwide were using operational models, essentially simpler twins, to predict ICU bed demand, ventilator needs, staff shortages during surges. It highlighted the need for these simulation tools for crisis preparedness, not just day-to-day efficiency.
Okay, from the hospital to the entire city. Segment 3.3, smart cities and infrastructure. This feels like the ultimate complexity challenge for a twin.
It really is. A city digital twin aims to be a dynamic 3D model integrating, well, almost everything. Buildings, roads, public transport, utilities like power and water, environmental sensors, even models of population movement.
Where's the leading example of this?
Virtual Singapore is probably the most famous. They undertook this massive project to create a highly detailed, high-resolution twin of the entire city-state.
How detailed are we talking?
Down to centimeter-level accuracy for the 3D geometry, using techniques like aerial laser scanning. LiDAR. So they have the precise shape of every building, every road, every tree.
But that's just the static map. What makes it a twin?
It's the layers of dynamic, real-time data overlaid onto that 3D model. Live traffic flows from sensors and GPS, public transport locations and loads, air quality readings from monitoring stations, noise levels, even anonymized data showing how crowds are moving through the city.
Which allows for powerful what-if planning. Like proposing a new skyscraper.
Exactly. Planners can drop the virtual skyscraper into the twin. The system then simulates the impacts. How will it affect traffic patterns on nearby streets? How will it change wind conditions at street level, important for pedestrian comfort and safety?
And shadows. That's always a big issue.
Calculates the shadows it will cast on neighboring buildings throughout the day, across different seasons. You can visualize and quantify these impacts before any ground is broken. Allows you to iterate on the design virtually, maybe change the orientation or height to minimize negative effects.
Saves costly rework and fights with the community later on. What about disaster management?
Crucial application. Simulate a major flood scenario based on predicted rainfall. The twin shows which areas inundate, how deep the water gets, and critically, which specific pieces of infrastructure are at risk.
Like power substations or hospitals in the flood zone.
Right, or key communication nodes. This allows emergency managers to prioritize defenses, preposition resources, and plan evacuation routes more effectively, all based on the simulation.
And cities are complex underground too.
Hugely important. The twin maps the incredibly dense network of buried utilities, power lines, water mains, gas pipes, fiber optics, sewer tunnels, subway lines. It's often poorly documented in reality.
So for any digging or construction,
The twin is invaluable. It helps planners avoid accidentally cutting a critical cable or pipe, which can cause chaos and cost millions. It visualizes the underground congestion before you excavate.
okay, final application area. Segment 3.4, energy and utilities. Reliability and efficiency are king here, especially with the shift to renewables.
Digital twins are becoming indispensable across the energy value chain. Power generation assets, gas turbines, wind turbines, solar farms, and managing the grid itself.
How does a twin help optimize, say, a big gas turbine in a power plant?
The twin monitors hundreds of parameters in real-time: combustion temperatures, pressures, vibrations, fuel flow. It runs physics models alongside the real turbine.
To predict failures.
Predict failures, yes, enabling predictive maintenance like we discussed, but also to optimize performance continuously. Companies like GE Vernova use twins to fine-tune operations.
Fine-tuned for efficiency, but also for emissions.
Exactly. The twin can simulate thousands of tiny adjustments to fuel mix or combustion parameters to find the sweet spot that minimizes pollutants like NOx and CO2 while maintaining maximum power output. That optimal setting can then be fed back to the real turbine.
That wind farm case study was striking. Software changes leading to real money.
Yeah, that was a great example. A large wind farm, maybe 200 turbines. They used a combination of detailed physics models simulating airflow around the blades and AI trained on historical weather and performance data.
And they were optimizing blade pitch and direction.
Right, for every single turbine. Because the ideal settings aren't just about the wind hitting that one turbine, it's about the complex interactions between turbines, how one turbine's wake affects the wind hitting the turbines downwind.
A complex farm-level optimization problem.
Very. And the twin figured out optimal settings that were slightly different from the standard factory defaults for those conditions.
Resulting in
A 2.9% increase in energy output per turbine seems small, but across 200 turbines year-round, that added up to an extra 32,000 megawatt hours per year.
which translated to millions in extra revenue.
Up to 2.2 million annually, purely from smarter, twin-guided software adjustments. No new hardware.
That's incredibly compelling. And for the grid as a whole, managing renewables.
Grid twins are essential now. They model the entire network: transmission lines, substations, power flows, voltage levels, frequency in real time. It's incredibly complex.
And they use it for contingency planning, the what-if scenarios.
Constantly. What happens if this major transmission line suddenly trips offline due to a storm or fire? The twin simulates the immediate impact, how power reroutes, where voltages might sag or spike.
So operators can test their response strategy virtually first.
Exactly. Before they implement changes on the real grid, they validate the stabilizing actions in the twin. This is absolutely critical for managing the inherent variability of wind and solar power while keeping the grid stable.
This move towards twins, not just advising, but actively optimizing. That leads us perfectly into our final segment. Segment 4, future outlook and emerging trends. Where does this go next?
The big immediate trend is more autonomy. Twins moving beyond just decision support to actually taking autonomous action, that closed-loop control we talked about.
So the twin becomes the brain, making real-time adjustments without waiting for a human.
Exactly. Imagine an autonomous twin running a complex chemical process. It detects a subtle drift towards an undesirable state and automatically adjusts multiple valves and temperature controllers simultaneously to bring it back into optimal parameters. No operator intervention needed.
And for self-driving cars, this must be central to their development.
Hugely central. Autonomous vehicle twins are essentially virtual copies of the car, its sensors, its AI driving software. They run simulations of millions, even billions of virtual miles driven in complex synthetic environments.
Learning from virtual mistakes mistakes.
Learning from virtual crashes, near misses, edge cases, and using that data to automatically tweak the car's design or update the AI's control logic. It's how they accelerate the validation of safety systems far faster than real-world driving alone could achieve.
That idea of self-optimizing systems points towards connecting individual twins together, right? The Federation of Twins or IoT.
Yes, that's the next level of complexity and value. System of systems modeling. Instead of just a twin of a building or a twin of the power grid, you connect them.
So the building twin talks to the grid twin, which talks to the traffic twin.
Precisely. They share data and create a larger composite model of the whole ecosystem. This unlocks insights and coordination that isolated twins can't provide.
Give us an example of that federation benefit in a smart city.
Okay, imagine a major power outage hits a section of the city. The grid twin detects it and instantly notifies other relevant twins.
Like the traffic system.
Right. The traffic twin, now aware of which traffic lights are out, can automatically adjust signal timings on surrounding routes to manage the disruption. It could also reroute emergency vehicles more effectively.
And building twins.
Building twins could be notified to switch to backup power only for essential services, conserving fuel, based on information from the grid twin about the expected outage duration. It enables coordinated cross-sector resilience.
Which is vital for big national strategies, like Japan's Society 5.0 idea.
Absolutely. Modeling those complex interdependencies is key to smarter infrastructure planning and management at scale.
And what about the role of more advanced AI, like generative AI, going forward?
It will continue to accelerate the what-if exploration, generating thousands of novel design options or system configurations for the twin to evaluate. But AI will also be crucial for managing the twins themselves.
How so? Keeping the twin accurate.
Exactly. With potentially terabytes of data flowing in, AI can help automate the process of refining the twin's parameters, identifying data anomalies, and ensuring the model stays synchronized and predictive, making the twin more self-aware and self-maintaining.
Okay, and underpinning all this future potential are those two ongoing needs, standardization and security.
They have to keep pace. Better standards mean easier integration, lower costs, and broader adoption, especially for smaller companies. Common data formats, open APIs, agreed reference architectures are all vital.
And security.
Yeah.
If the twin is the brain, it's a prime target.
A huge target, especially for critical infrastructure or healthcare twins. Protecting the data feeds, securing the twin platform itself, ensuring the commands sent back to the physical world are legitimate. It's a massive cybersecurity challenge that's getting intense focus.
Which leads maybe to the ultimate ambition, twinning the entire Earth.
It sounds audacious, but initiatives like Europe's Destination Earth are genuinely working towards that, creating a highly complex digital twin of the entire planet system, atmosphere, oceans, ice, land.
To simulate climate change with unprecedented accuracy.
That's the goal, to model different climate scenarios and test the potential impact of various mitigation or adaptation policies with much higher fidelity than current models allow, giving policymakers better tools.
And finally, bringing it right back to the individual. The ultimate personal twin, a full digital avatar.
That's the long-term, perhaps most revolutionary vision. A dynamic twin incorporating your genetics, your full medical history, your lifestyle choices, fed by real-time data from wearables.
Acting as a lifelong, personalized health coach and predictor.
Exactly. Moving healthcare from reactive treatment of sickness to proactive, continuous management of wellness, guided by your unique virtual self. It's a profound shift.
What a journey we've covered today. From NASA engineers using physical simulators to save Apollo 13.
Through Gellenter's vision and Greaves' formalization.
To today, where these twins optimize global supply chains, make jet engines greener, help surgeons practice complex operations.
And manage the complexities of our cities and power grids, it's become this essential feedback loop between the physical and digital worlds.
Driving efficiency, resilience, innovation.
Absolutely. The digital twin is really a cornerstone of digital transformation, enabling systems to learn, adapt, and optimize themselves in ways we couldn't before. The shift to self-optimization is well underway.
Which brings us to our final thought for you, the listener. We're seeing digital twins move from just reflecting reality to actively shaping it through increasingly intelligent and autonomous actions. So, if the virtual model is becoming the smarter, faster brain for the physical system, what does that mean when the systems in your life start making their own optimization decisions daily? Think about your commute, your energy use, maybe even your health. What could be improved if it could be perfectly modeled, simulated, and optimized continuously